Large language models can now write custom, high-performance CUDA kernels. For engineers looking to accelerate machine learning workloads, agentic generation looks like an immediate solution. But the existing tools built to harness these models rely on a flawed evaluation standard. They measure performance using randomly generated tensors and isolated kernel invocations. A standalone kernel might dominate a synthetic benchmark, but stitch that exact code into an actual PyTorch model running in production, and it often severely regresses performance. The problem is context. An isolated benchmark never sees the model-specific tensor shapes, the true distribution of activations, or the memory state left behind by neighboring operators. This graphic shows the disconnect. On the left, a benchmark environment processes uniform data. On the right, a deployed PyTorch model operates as a sprawling execution graph. Dragging the isolated kernel into the live model destroys execution speed. To solve this, engineers must stop optimizing kernels in isolation. The optimization target has to be the exact execution path captured from inside a running model. This is exactly what Kernel Forge does. It is an open-source agent harness designed to close the gap between synthetic benchmarks and deployment realities. It operates on 3 pillars: capturing exact variance from real execution traces, navigating a Monte Carlo tree search to optimize them, and applying strict performance guards before deployment. True systems optimization relies on the live model's execution path as the ground truth. Measuring isolated kernels against random data simply does not predict real-world value. The Kernel Forge pipeline begins with ingestion. You provide an unmodified PyTorch model and example inputs. The harness runs an inference pass while a profiler observes. The profiler records every supported operator that executes. For every individual call, it extracts the exact tensor shapes, D-types, strides, memory layouts, and example inputs and outputs. This data defines the core unit of optimization, the variant. A variant is a concrete, observable operator case. It is not an abstract public name like convolution or softmax. If a model calls the same operator twice, but the tensor shapes or arguments differ between those calls, Kernel Forge treats them as entirely distinct variants. The ingestion phase outputs this structured data as an operator card. It summarizes the call count, its share of the model's total runtime, and its exact shape and D-type manifest. Crucially, this card records the PyTorch eager execution latency. This preserves the original baseline performance, providing an absolute reference for all future checks. By optimizing these concrete variants, the agent is forced to solve the specific math the model actually computes in deployment, rather than a generalized approximation. With the operator card defined, a large language model agent takes over, attempting to write custom CUDA source code and a launch wrapper for the variant. Every candidate generated by the agent must survive this rigid, deterministic validation pipeline before it can enter the search tree. If the code fails to compile with NVCC, crashes on launch, or produces a numerical mismatch, the harness routes the specific error data backward into a bounded work-care loop for the agent to try again. Success is defined strictly by the numeric check. The generated kernel's outputs must match the PyTorch eager outputs captured during the ingestion trace, within an accepted tolerance. But passing this check comes with a critical limitation. This validation is strictly a workload-specific filter. The kernel calculates the correct answer for the inputs captured in the trace, but it is not mathematically proven to be correct for all possible inputs. The Forge loop trades universal applicability for guaranteed safety on the target workload. If the kernel works for the captured trace, it is admissible. Validated candidates are benchmarked and inserted into a persistent Monte Carlo revision tree. Each variant gets its own isolated tree. Each node in this tree represents a candidate kernel, tracking its source code, its parent and child links, its visit count, and its measured execution latency. You might expect the system to immediately discard the slow orange nodes. Instead, Kernel Forge deliberately retains them. A locally poor-performing kernel might contain an interesting memory layout or a structural seed. If the agent revisits it later, it can spark a highly optimized revision downstream. To find those optimal revisions, the agent controller navigates the tree using 2 mathematical rules to select its next target. The first rule is progressive widening. This formula dictates how many children a node is allowed to have, based on its visit count.
Early in the search, the alpha parameter allows the nodes to branch broadly. As the search deepens, alpha anneals from 0.5 down to 0.3. This mathematically caps new branches, forcing the controller to reuse and refine existing paths. When descending a branch, it applies the second rule, a minimization UCT formula, scoring the child nodes to determine exactly where to explore next. Standard UCT adds an exploration bonus. Because Kernel Forge is trying to minimize latency, the sign is inverted. Subtracting the bonus lowers the score of rarely visited nodes, making them more mathematically attractive to explore. The first term, LC, pulls the search towards subtrees that have already proven to be fast. The subtracted second term pushes the search toward untouched branches. By retaining slow candidates and navigating them with strict UCT logic, the tree avoids getting trapped in local performance minima, steadily uncovering globally optimal CUDA code. Once the per-variant search budget is exhausted, Kernel Forge exports the optimal candidates into a deployable package. The execution of that package in production is controlled entirely by a policy called guarded dispatch. For a generated kernel to execute instead of the default PyTorch path, it must pass through these 4 sequential gates. It must be available, compatible with the call, numerically valid for the workload, and definitively faster than eager. If all 4 conditions light up green, the model uses the custom CUDA. If a single gate fails, the routing defaults entirely to the original PyTorch eager path. Because this decision is evaluated independently for every variant, Kernel Forge can mix custom code where it wins, while relying on the highly optimized eager implementations everywhere else. Every path is then tracked using audit labels, categorizing the execution as custom CUDA, a backend wrapper, or a fallback. Agents frequently generate wrappers that secretly delegate the math back to vendor libraries like QBLAS. The audit labels exclude those wrapper paths from generated CUDA win claims, keeping the final performance metrics honest. Guarded dispatch takes the inherently unpredictable output of a large language model and structures it into a mathematically guaranteed, non-regressive software artifact. When evaluated across 4 distinct PyTorch models, spanning vision, diffusion, and LLM inference, 14 agent-generated kernels outperformed their eager execution baselines. The peak isolated success was a 2.83x speedup on the softmax operator within the Gemma 4E2B model. But to understand the true impact, we have to look at this chart. The softmax speedup is massive, but it only accounts for 5.93% of the model's total runtime. The data reveals a clear discrepancy. The agent succeeds on open-source native operators that take up very little compute time. The dominant operators, like linear layers and convolution, which consume 90% of the runtime, are backed by mature proprietary vendor paths. The agent consistently fails to beat them, hovering at just a quarter of the eager baseline speed. This proves why guarded dispatch is a structural necessity. If you deployed generative kernels blindly, replacing a 90% runtime operator with code that runs 4 times slower, you would cripple the entire model. Integrating AI into systems programming requires discipline. Measure your generated code against the real live model, isolate the specific variants, and only ship the resulting code behind an impenetrable performance guard.